Have you ever really stopped to look at a satellite dish and wonder how it all works? I mean, how does a TV show get from a studio up into space and then back down into your living room? It's this wild mix of physics, clever engineering, and what honestly feels like a little bit of magic. So let's follow that signal step by step and demystify the entire journey. The whole idea of a global satellite network feels so modern, right? But it was actually dreamed up by the legendary science fiction writer Arthur C. Clarke way back in 1945. What was once pure sci-fi is now just a normal part of life for millions of people. And yeah, that science fiction is literally sitting on your roof right now. So how does that piece of hardware pull it off? Okay, let's really dive in. We're going to trace the signal's incredible journey from the cold of space right down to your TV screen. All right, so our journey begins way, way up there. We're talking 22,300 miles above the Earth with a geostationary satellite. It's beaming down thousands of channels 24/7. But here's the catch. After traveling that enormous distance, the signals that actually reach us are incredibly faint microwaves. They're so weak, you need a very special kind of tool just to catch them. And that special tool, that first stop on the ground, is the satellite dish. You've seen thousands of them, right? It's the most obvious part of the whole system, but what it actually does is one of the most misunderstood parts of the process. So let's just ask the question straight up. I mean, it looks like an antenna. Is it just pulling signals out of the air, like an old radio? Well, the answer is not quite. It's actually a lot more clever than that. The best way to think about a satellite dish isn't as an antenna at all, but as a big, perfectly curved mirror. But instead of reflecting light so you can see your reflection, it's designed to reflect those super faint radio waves coming down from space. The secret is all in the physics of its shape. The dish has a very specific curve. It's a parabola. And what that shape does is brilliant. No matter where those weak signals hit the surface, they all get bounced and reflected to one single tiny focal point. It's a lot like using a magnifying glass to focus sunlight into a tiny, hot dot, but you're doing it with invisible radio waves. And right there, at that focal point, you'll see this little thing hanging out on an arm. This small device is the real hero of our story. This is where the actual magic happens. It's called an LNB. That stands for Low Noise Blockdown Converter, which is a mouthful, but its job is pretty straightforward. It does two crucial things. First, it takes that now focused but still very weak signal and gives it a massive boost. It amplifies it. And second, it translates or downconverts that signal into a language or frequency that the cable running into your house can actually handle. And this is a serious transformation. The signal coming from space is at an incredibly high frequency. It's just too fast for a normal cable. The LNB's job is to take that signal, amplify it, and slow it down to a much lower, more manageable frequency that's ready to travel indoors. But just how dramatic is this change? Well, get this. This signal arriving from that satellite can be buzzing along at up to 12,700 megahertz. And after the LNB works its magic, that signal is brought all the way down to a maximum of 2,150 megahertz. That is a huge difference. So you might be wondering, okay, why go to all this trouble? Why can't the cable just carry the original signal? Well, that brings us to the next leg of the journey, and it's a really important one. So the signal's been caught by the dish, it's been amplified and translated by the LNB. Now it has to make the final trip from the dish on your roof through a standard coaxial cable and into your living room. So here's the crucial point. A coaxial cable is basically just a copper wire, and those really high-frequency signals, like the original one from the satellite, they lose their energy, their strength, very, very quickly when they travel through a physical cable. This process is called attenuation. The original signal would basically just fade into nothing after only a few feet. So by down-converting it, the LNB creates a tougher version of the signal that can actually survive the entire trip to your TV set. Okay, so that's how the signal gets into a single house. But what about bigger buildings? Apartment complexes, hotels. You never see hundreds of dishes bolted to the roof. So how does that work? The logistics might seem like a nightmare, but the solution is actually pretty elegant, and it builds on the very same principles we've just been talking about. It's done with something called an IRS, or an integrated reception system. The easiest way to think about it is like a tiny private cable company that serves just one building. It takes all the signals from one central dish and then distributes them efficiently to every single apartment. So here's a quick breakdown of how it works. A special kind of LNB captures all the different signal bands at once. Then, a launch amplifier gives that signal a massive power boost for the long journey through all the building's wiring. After that, a series of multi-switches act like traffic cops, directing the correct channels to each apartment's wall plate. Pretty clever, right? This journey from a satellite to a dish to an LNB and down a cable has been the gold standard for decades. But, as you know, technology never ever stands still. The way we get our signals is constantly changing. And today, that journey is changing again. Now we've got technologies like fiber optics, which send the signals as pulses of light through glass strands with almost zero loss in quality. And then there's IPTV, which basically turns your TV channels into internet data, delivering them over the very same networks you use for web browsing. The signal's journey is merging with the internet itself. So when you think about it, from a visionary idea sketched out in a magazine in 1945 to the high-tech dish on your roof today, and onto the fiber optic cables of tomorrow, the signal's journey never really ends. It just keeps getting faster, clearer, and more innovative. It really makes you wonder, what's the next chapter going to look like?